Hello, everyone, and welcome back. So here we're at 613, and now this lesson is just about practicing what we have just learned, which is the derivatives of exponential functions. So quick little recall is what we learned leading up in this chapter is we learned what E is, which again is approximately 2.71828, and it's a very special number when things get compounded continuously. And then we talked about how E is natural in the sense that we first learned that when you take the derivative of e to the x, it stays e to the x. Unlike every other type of exponential, when you put in a 2 or 3 there, it's not the same thing. But there is some number in front. But with e, that number in front is 1. Now what makes it 1 is we soon discovered that if e is the natural exponent, then the inverse of e to the x is natural log of x. Right, so these work hand in hand. So these are inverses of each other. But all that leading up to is what we discovered is the following. To take the derivative of an exponential function, say a to the x, we learned that it's going to be the natural log of the base is your constant in front times that same function a to the x. And that is what's going to allow us to differentiate even more functions. The toolkit is getting so heavy. There's so much you can differentiate now. You have exponentials, polynomials, trig functions. Don't forget about the product rule, the chain rule, the quotient rule. Those 6, we pretty much have everything. The only thing missing is log functions, which we're going to be getting to soon. So let's look at just some examples using this now. Just don't forget about the chain rule, which I can't spell. The chain rule states that for a function that's made up of functions, or a function that has a composition of functions, f of g of x, the derivative is going to equal the derivative of the outside, leaving the inside alone, times the derivative of the inside. All right, now I say that aloud, and I hope you can say that to yourself as you do these problems, because the chain rule comes up all the time. So example 1, take the derivative of e to the 2x. So notice, we know e stays the same, but let's just use this definition. So it's the natural log of the base times that same function, e to the 2x. However, chain rule kicks in here. The derivative of the outside, so the derivative of the exponential, leaving the inside alone, times the derivative of the inside. Well, what's the derivative of 2x? That's just 2. So then this gives us 2 times natural log e times e to the 2x. But remember, natural log and e are inverses, or natural log has base e. And this is just going to go to 1, because e to the first power equals e. So your final answer here is actually just 2e to the 2x. Because again, don't forget about that chain rule. Looking at the second example, take the derivative of 5 to the cosine x. So it's an exponential raised to a power of a variable. So it's going to be the natural log of the base times that same function. But because of chain rule, the derivative of the outside, leaving the inside alone, times the derivative of the inside, and the derivative of cosine x is negative sine of x. So there's your answer. We'll just clean it up. I like to put this at the end, so I'm going to push that in front, or after the natural log 5, because that's just a number. So you have a constant, put a negative there, times sine of x, times 5 to the cosine of x. And there's your answer to that example. Example 3, take the derivative of 2x e to the 5x. Now this one's going to be a bit longer, and I kind of messed myself up by not giving much space, because this is actually product rule, because it's 2 things multiplying together. So it's the first times the derivative of the second, and the derivative of e to the 5x is natural log of e, but again, I'm not going to put that because e we don't need to, it's just 1. So times natural log of e times the function itself, and then because of chain rule, take the derivative of the inside, which would be 5. So the first times the derivative of the second, plus the second times the derivative of the first, which is just 2. And there's your answer. Cleaning it up a little bit, we'll have 10x e to the 5x plus 2e to the 5x. That's a cleaner way of writing that. Good. Example 4, we have 7 times 4 to the x squared. I made some mistakes when writing this out. Now remember with derivatives, I put this example here is because constants front we can pull out in front. So this is actually equivalent to saying 7 times the derivative of 4 to the x squared. You can keep the 7 there if you want, but sometimes it's nice to pull that out. So then we'll have here 7 times natural log of 4 times 4 to the x squared. But because of chain rule, take the derivative of the inside, the derivative of the outside, leaving the inside alone, times the derivative of the inside, which is going to be 2x there. So cleaning that all up, I would have natural log of 4 times 14x times 4 to the x squared. And that's the derivative function of that. And then my last example, just as a reminder of quotient rule, we would have here the bottom times the derivative of the top, which would be natural log of 4 times 4 to the x, in which you could do chain rule still. What's the derivative of x? That's just 1, but we don't need to write that. Minus the top times the derivative of the bottom all over the bottom squared. So notice how I have these sayings memorized, and that's why I highly recommend you do the same thing with product rule, chain rule, and quotient rule, because those come up a lot in calculus, and you want to know how to handle that situation. Cleaning this up, I'll just put the natural log 4 in front, then the times the 2x minus 1 times 4 to the x minus 2 times 4 to the x all over 2x minus 1 squared. Doesn't look cleaner, but say it's a little cleaner. But there you go. So there's some examples of using the derivative of an exponential function, which we have learned from the past day. Okay? If you have any questions, make sure you reach out. Bye-bye.